Well, it's week 2, and this week we're going to talk about minerals, and we're going to look at minerals down in the lab. So the PowerPoints this week, the slides, are going to focus on the stuff that you need to know about minerals, um, except for the physical properties and mineral identification. So this is a lot of a background information to kind of tell you what's going on, and then in the lab we'll have the hands-on. So first of all, what is a mineral? So these are some questions you want to think about. What are the important physical properties of minerals? And why do different minerals display different physical properties? Those are some questions you might want to have in your mind as we go through this week's material. So let's start out with what is a mineral. A mineral is defined as a solid, naturally occurring, inorganic crystalline substance with a specific chemical composition. And what I would point out here is that in order to be crystalline, it has to be solid. So really you can kind of ignore the solid part because that is inherent in crystalline. Naturally occurring is kind of an interesting little property because we can make synthetic minerals. We can make synthetic diamonds, synthetic quartz, we can make all kinds of minerals. And in fact, it turns out that mineralogists, when they want to do research, very often will make a mineral because the naturally occurring minerals usually contain impurities. Whereas if you craft something in the lab, you can make it pure and find out exactly what its properties are. So if you want to study it, it turns out you're actually a little better off making your own because you can control the conditions of formation. Inorganic is another kind of interesting little part of the definition, and that is because there are certain minerals that are very commonly used by living organisms. And the best example of that is a mineral that we're going to encounter a lot, which is the mineral calcite. And shellfish, like clams and oysters, and other organisms like coral, use calcium carbonate to make their shells. Now, technically, by this definition, those shells are not considered minerals because they're organic in origin. They're made by a living organism. So the first 3 parts of this definition, I always bring up questions about them in class because they are they're a little extra. The last 2 are the ones I always like to focus on because if you look at a mineralogy book, the way we define a mineral, the way a mineralogist defines a mineral, is by the mineral's specific chemical composition and its crystalline structure. And we'll talk a little bit more about that later in the presentation. So I want you to kind of keep that in mind, that really the key parts of this definition are crystalline and specific chemical composition. You can make minerals in the lab. We just call them, we don't call them minerals, we call them essentially a created mineral or a synthetic mineral. But it still has all the same properties and everything. And inorganic is, again, like I said, kind of arbitrary because we know that there are living organisms involved in the creation of minerals and in many cases using them to make their shells. So unless you know the origin of the mineral, it's hard to say if it's organic or inorganic. Most minerals are inorganic, but there are some important ones that are organic. So enough of that. Let's go on to rock. So what is a rock? I think the best definition of a rock that I've come across is the one I have on here. A solid aggregation of earth materials. So when we think of a rock, we think of something that is solid, something that is hard, and is made of earth materials. Now you'll notice on the bottom it says comprised of minerals, and in most cases rocks are just made of minerals. But because of the specificity of mineral definition, a rock that's made of organic materials, and in the bottom of this slide you can see that particular rock is made of shells, technically is not made of minerals. Remember, that was ruled out. It's got to be inorganic. So if it's made of organic materials like shells, it's not technically made of minerals. So to avoid that, if we just say earth materials, we can include plants and shells and other things. In addition, plants are not crystalline. So if you have a piece of coal, it's made of organic material from the wood. There are no crystals involved at all, so it's definitely not a mineral. And we also have some rocks that are made of what we call amorphous material, which is glass. So volcanic glass and a lot of volcanic ash is made of little tiny bits of glass. Those amorphous materials are not technically minerals because they don't have a crystalline structure, and they may not even have a specific chemical composition. It could be kind of a mishmash. So all that stuff counts as a rock, and that's why we have the definition that's kind of vague, a solid aggregation of earth materials. Now, I might add naturally occurring to that to rule out things like asphalt and concrete. But solid aggregation of earth materials is a nice, simple definition for rocks. So let's look at the connection. Most rocks are made of minerals. And so to show you that linkage, if you look at this picture on the left, that's a photo of a rock, the pennies for scale. If you look at that under a microscope, if you make a really, really, really thin slice and put it under a microscope, the light can shine through the mineral crystals and it looks like the picture on the lower right. And so you can see all of the individual and different mineral crystals that are present in that rock. And so generally speaking, rocks are made of minerals, but again, they're very often made of other materials as well. So where do these minerals come from? Well, minerals form when you have unbonded atoms. So think of the periodic table of the elements. I could have included a slide of that in here. Everything from hydrogen and helium up to oxygen and silicon, iron, gold, uranium. All of those things are atoms. And under certain conditions, they are not bonded to anything. They're just kind of moving around. And on Earth, where we typically find those conditions would be when the rock is very, very, very hot. So hot that it's melted. Molten rock or liquid rock, that condition indicates that the atoms are moving very, very quickly. And because they're moving quickly, they're not able to bond with each other. They're not able to form a solid. Likewise, if you have a solution, typically involving water, if we're looking at kind of natural environments, the unbonded atoms are basically kind of isolated from each other as dissolved materials in the water. And to get them to bond, if you have the molten rock, you cool it down. And when you cool it down, the motion of the atoms slows down. And as molecular motion slows, or the motion of those atoms slows, they are able to hook up with each other. Think of a good example would be if you went to a dance. When the music is fast, people are kind of dancing around the dance floor. They're not touching, they're not bonded. And when the music slows down, couples will tend to pair up and dance together, and so you have some bonding there. That's basically what happens with the unbonded atoms. When the temperature goes down, they are able to link up with other atoms under certain conditions and form, in the case of minerals, they're able to form crystals. If we have things dissolved in solution, you have to do something typically to that solution to allow bonding to occur. And very often what happens in a natural environment is that the water evaporates. If we're looking at organic material, the ions could be linked up within the body of a living organism. So, for example, your body makes teeth and bones. And if you're looking at something like a clam, it's able to construct a shell out of those dissolved ions. Otherwise, if the water evaporates, the water was separating those ions from each other. As it goes away, they're able to find each other and link up and form bonds. So that means one of the key topics that we want to take a look at is chemical bonding. And the way chemical bonding works is described in great detail in your textbook, and I encourage you to look through your textbook to get that information. But basically, electrons in the outer shell of an atom are shared or exchanged. This provides stability in that outer electron shell, and it results in several different types of chemical bonds. These two are the most common types of bonds, the covalent and the ionic bond. The covalent bond occurs when electrons are shared, and this is considered the strongest type of bond. A hydrogen atom, and two of them are here, they're in green, has one electron in its outer shell. The oxygen atom, which you can see here in kind of a purple color, has, when it's all by itself, 6 electrons in its outer shell. When they come together like this, they are sharing their outer shell electrons. It fills up the outer shell of the hydrogen with 2. And you'll notice that the first shell in the oxygen has 2 already. And then the oxygen, by bonding with 2 hydrogen atoms, ends up with 8 in its outer shell, and that's referred to as the octet rule. Typically what we see in the outermost shell of many atoms is room for 8 electrons. And so that's why we have H2O as our really common molecule. It's water. HO does exist. H2O2 exists, but they're not as common. They're both actually pretty reactive because they're looking to fill some vacancies in their outer shells. H2O is a very, very stable atom, and it's very strongly bonded. It takes a lot of energy to pop the hydrogens off of the oxygen. So in the lower right, we have an ionic bond. This is a little bit different process going on. Naturally, chlorine has 7 electrons in its outer shell. It's got 1 vacancy. And sodium, which is on the right, has 1 lone electron in its outer shell. So what happens in this case is sodium gives up its electron. It then has the next shell in, which is completely full. It's got 8, so that's stable. Chlorine picks up that extra electron, adds it to its outer shell, and it is complete as well. However, the result of this is that sodium ends up with a positive charge because it's missing 1 electron. Chlorine ends up with a negative charge because it's got an extra electron. And because they have opposite charges, they're attracted to each other. And this results in the formation of what we call ionic bonds. The next 2 bonds that we're going to show you, a little less common, but still pretty common, we find them in a lot of minerals, are metallic bonds where the electrons kind of roam around, and what's referred to as van der Waals bonds, which is driven by the intermolecular force. And you'll notice it's got some sheets of atoms here that are actually bonded together more strongly, but between the sheets is where you find the van der Waals bonds. And that pretty much wraps it up for this. What we're going to do is I'm going to take a little break. There'll be a second, somewhat shorter video that's got the rest of the presentation on it, where we talk about mineral identification